One final way that we can try to write vectors as either a linear combination or in the component form is we can write them as a combination of trigonometric functions. And of course, we remember that the cosine is the x, the sine is the y coordinate. Okay, so we're going back to our trigonometric definitions. And we certainly know if it's a unit vector, well, that means it has a magnitude 1, which means that the vector, if I called it v, right, and it would fall somewhere on the unit circle, okay? And so if this is the point, the terminal point, then remember that's the cos of theta, sine of theta, okay? And it has magnitude 1. And so if I really wanted to, I could write it like this, or that would be the same thing as cos theta I plus sine theta j if I wanted to write it as a linear combination. Now, what if it's not a unit circle, okay, or not a unit vector? Well, all I'm going to do is just multiply that by the magnitude v. And so if u is not a unit vector, it has magnitude v, then we could just write it as magnitude v cos of theta, magnitude v sine of theta with I and j, multiplying by those unit vectors in the directions of x and y. So really easy problems to do. Let's say we had magnitude is v and theta is 60 degrees. Okay, so let's just say over here that for some reason this was a 60-degree angle and we had a magnitude of 8. And so the way that I would write this, vector v would be equal to 8 cosines of 60 degrees, I, plus 8 sine of 60 degrees, j. We would certainly evaluate the sine and cosine. Okay, so this would be 8 times root 3 over 2i. I'm sorry, 1/2 for the cosine of 60. So I was going the opposite way. All right, so this is a half, and then plus 8 times root 3 over 2j. All right, and again, that's just by using our unit circle to evaluate the sine and cosine at 60 degrees. And so finally, I could simplify this into 4i, since that's half of 8, plus 4 roots of 3j. Now, not all of them are going to work out exactly. All right, so let's say we had something like magnitude v equals 1/3 and theta is 127 degrees. So that would mean that my vector v would be equal to 1/3 cosine of 127 degrees, I, and then plus 1/3 sine of 127 degrees, j. Now, in our calculators, it says to approximate these values accurate to the nearest hundredth. Okay, so we're going to take 1/3 of the cosine of 127. So that gives us negative 0.20. Okay, so that's going to be negative 0.20i. And then if we took 1/3, and I'm just going to change this to a sine, that's going to be 0.27. Okay, so plus 0.27j. All right. So if it's not like an exact angle, okay, or one of the ones that we can look at the unit circle, that might be the easiest way for us to be able to try to evaluate. One last sort of thing that we can do is we can find the direction angle produced by a vector in standard position. Okay, so let's say for some reason we had our vector and it looks something like this, and we had an angle theta. Okay, well, we remember that one way to write it would be whatever the magnitude of v is times I, okay, in that direction, or the cos of I, okay, so magnitude in the x direction would be magnitude v cos theta I. Oh, this, and then, so if this is the point right here, the terminal point, then we could say that we could actually get a triangle out of this, okay? And we know that this would be the magnitude of v cosine. This would be the magnitude of v sine theta j, right? And of course, we know that this has a unit vector of 1. And so if we really wanted to, we could take the relationship of theta to the opposite over the adjacent side, and we could just get a really nice tangent function. Okay, sine over cosine is the ratio of opposite to adjacent. So we could say that theta of u sub 2 divided by u sub 1 is going to be equal to the, or in other words, we can find our angle, or the angle is going to be the arctangent of whatever this coordinate is. So let's just say that this is the coordinate u1 comma u2, which could be written like that. All right, so let me show you how to do this. It's actually pretty easy for us to do. All right, so we're going to go ahead and try to find the direction angle. All right, we're going to approximate to the nearest angle or nearest degree if necessary. Okay, so what we always want to do first is plot it. Okay, so we know square root of 12 is a little bit more than 3. All right, so if I'm plotting this, okay, maybe something like this. Okay, so when we get our theta, it should be in quadrant 1, right? And so what we're going to do is we're going to take the inverse tangent of the y coordinate divided by x, because remember, tangent is y over x, okay? And unfortunately, I don't know if this one works out nicely. Now, we do know that 12 is the square root of 4 times 3, square root of 4 times square root of 3, so this would be 2 roots of 3. And so this would become the inverse tangent of 2 roots of 3 over 2. The 2's would cancel out. And the inverse tangent of root 3 is either pi thirds or 60 degrees. Okay, and that's one that we've had memorized for a long time, okay, since our inverse functions. Okay, of course, you could always just go in your calculator and you could just clear it out and just do the inverse tangent of 60 or the inverse tangent of square root of 3, and you'll see that it just goes to 60 degrees. So that's another way to do it, whichever you prefer. Another example, so we're going to find the arctangent, and be careful with this one, of y over x, so that's going to be negative 1008 divided by negative 1008. Now, when we plot this, okay, if we plot 1008, 1008, it's the same x and y coordinate, okay? So this is going to be our angle when we get something, okay? So whatever angle we get, it should terminate in quadrant 3, all right? But we know that this is going to be the inverse tangent of 1, and we know the inverse tangent is pi fourths, okay? That means that we have a reference angle of pi fourths, okay? So this little angle right here is actually pi fourths. So what we have to do is we just have to add pi to get to the rest of it, okay? So it is important for us to go through and make sure that when we get these angles, we realize that sometimes we get reference angles, okay? So this is going to be pi fourths plus 4 pi over 4, or in other words, 5 pi over 4. All right. So a couple more examples. Okay, so this time we have negative 6 roots of 3, 18. Okay, so just as a basic estimate, okay, we know that negative 6 roots of 3 might fall over here, 18 might fall over here, so we get this, and this should be our angle theta. All right, so we should end up with an angle between 90 and 180, or between pi halves and pi. All right, so we're going to find the inverse tangent of 18 over negative 6 roots of 3, or that's going to be the inverse tangent of negative 3 over the square root of 3. And if we rationalize that, so negative 3 over root 3 times root 3 over root 3, that would be negative 3 roots of 3 over 3, or negative square root of 3. Okay, so that's the same thing as the inverse tangent of negative root 3, which we know to be negative 60 degrees, or negative pi thirds. All right, so that's a reference angle. Okay, so this is going to be the negative pi thirds that we end up with. So what we're going to have to do is we're just going to have to add pi to that, or that's going to be negative pi thirds plus 3 pi over 3. And so the angle should be 2 pi thirds. Okay, so we just have to be careful when we're doing this. We have to make sure that the angle makes sense. Okay, we're going to have to use those reference angles in the graph. Now, this one's not much we can do about it because it's not going to be a nice one. All right, so if we graph it, we know that 5 is over here, 6 is down here, and so this would be our vector. All right, and so we know that we're going to end up somewhere in quadrant 4. Okay, so our radian measure when we're done with it should be somewhere between 3 pi halves and 2 pi. To find this, we're going to find the inverse tangent of -6 over 5. Okay, so it's always y over x. Okay, so over here we just put the 18 over 6 roots of 3. This one's not going to be nice. There's nothing we can do about it. So let's just go into our calculators. Okay, and in our calculators, if we took the inverse tangent of -6 over 5, right, that gives us 0.0209. If we put it into radians, -2.57. Okay, so this is going to be our radian measure, -2.57. All right, and that's in radians. All right, so what we're going to have to do is we're going to have to add 2 pi to that. Okay, so if we took 2 pi minus 2.57, that should tell us what our value is going to be approximately in radians. Okay, of course we can get it in degrees if we really wanted to, but we're not going to. So if we do this, we just go into our calculator. Oh, and this should have been the inverse tangent, by the way. I think I put the tangent in there. So let's do that again. The inverse tangent of -6 over 5. Sorry about that. Okay, so that would be our radian measure. Okay, our degree measure is about -50.2. All right, so this is really -50.2 degrees. Okay, or in the radian measure, like we said before, that's going to be 0.888 or something like that. So, right, so if we went in our calculators and we just took 2 pi and we subtracted 0.88, that would be the radian measure. Okay, so theta would be approximately 5 point, we said 4 radians, or in degrees, we would take 360 and subtract out 50.2, all right, and that would give us 309.8 degrees, which makes sense because it should be somewhere in quadrant number 4. So this is our theta, 309.8 degrees. All right, so that's how we would have to try to work with those types that aren't nice in a unit circle. Okay, so that's everything for our vectors. Okay, key concepts to make sure of: make sure that you can add, subtract vectors, do scalar multiplication, find magnitudes, and then also make sure that you can find unit vectors in specific directions. Write them in terms of an angle. Okay, in the angular form, and then finally be able to find the direction angles of vectors.